do in preparation. Okay, so much for machine learning. Now you are all experts in machine learning. Let's talk about this specific case of regressors for deep learning. Okay, here we go. So now Yannet may differ from me on this, but what I found the neural network metaphor to be kind of, I don't know, it doesn't sink into my brain very well. But you have to know the terminology. This is the terminology that we all use. Okay, so you have to know. In my mind, we are simply gluing together a series of linear and nonlinear transformations. I'm taking a vector in one space and I'm moving it to a vector in another space. Might be bigger, might be smaller, but that's all I'm doing. These building blocks look like this. I have a linear layer, and if you want, you can ignore this layer. It's not really an exponent, but an attribute. So you can ignore the layer part here for a moment. A linear layer is taking an input vector, and as you can see, I'm rotating it here to get the transpose. It's just an instance, a record from my X. It's all the information I have about an apartment or an image, okay? And I'm transforming it to a new space by hitting it on the left with a matrix. And because that can be I can convert it to another vector, I need to have a vector of things I can shift it. So I'm like scaling it or rotating it and then shifting it. So it just gives me a certain amount of power. That's all I'm doing. So I have a linear transformation on this X. That's all that does. And we'll worry about the details of what's in here in a second. So once I have the output of this linear layer, I also have the option of gluing on a so-called activation function. And this is a nonlinear activation function. In this case, I'm just going to say, let's call it a sigmoid. You know, you're already familiar with a sigmoid. I'm just going to threshold everything between 0 and 1, and that is my nonlinearity. So these are our two building blocks, and we can do a huge amount with this stuff. So here is an architecture for a neural network. I take my record, a single record that I want to run through the network, and I tend to see these vectors as vertical, being shifted through the network. So it also makes sense from a math point of view, because you could, of course, put this on the left and then it would be this way, but this is just the way I look at it, but we're really just talking about linear transformations, so it's no big deal. Okay, so I'm sending in this vector. I'm passing it through a layer, and all that layer does is one of these duplicitous here. It converts it from a 2 vector to a 5 vector. And obviously we can come up with a matrix that does that. And you can think of all the B's as 0 if you want, it doesn't matter. But we're just transforming that space. And then I'm running it through a sigmoid, and of course I get something of the same dimensionality, but I've thresholded all the values inside. I run that into another layer, and that converts the 5 vector to a 3 vector. Why? Well, let's just say I knew I needed to do that, and I've played around, and it gives me a good validation there. Once again, I run it through a sigmoid, and I get something of the same dimensionality. My final layer takes a 3 vector and converts it to a 1 vector. So this is going to be just a row vector in this case. And I multiply it by this, and out comes a 1 by 1, which is my regression value. So the way I think of this is I'm taking the raw, it could be the raw pixels of an image, or I'm taking and I'll do it vertically, or I'm taking the characteristics of a loan application or something, or an apartment, and I'm gradually morphing these raw features into more and more sophisticated features until finally I get all the way to the end and I have a trivial linear regression problem that you've seen already. So you can, if you forget everything over here as just somebody with a lot of experience created really good features for me, and then I can just do linear regression and get a value out of it. That's the way I think of it. And so it allows me to break down and think about each of the layers as really just doing a simple transformation. All right, so let's look in more details at these building blocks. So we can do a huge amount with just 3 building blocks. I've got my linear layer, and I'm not going to put the T in there because it screwed up my visualization, but just assume that this is a block that represents a simple linear transformation on a vector. And then I've got 2 different kinds of nonlinearities. I've got a sigmoid and something called a rectified linear unit. This does nothing mathematically interesting other than any value that's less than 0, make it 0. It's just clipping. That's all it is. Now, it's kind of got this discontinuity here, but in the end, that works out numerically when we use it, and it's faster to compute than the sigmoid. And they've shown in many cases that this one, nonlinearity, is going to result in better networks. So anyway, but those are the 3 things we need. We'll still need the sigmoid. So you're familiar with linear regression equations. This is going to be beta 1, beta 2, and so on from your linear regression and beta 0. In vector multiplication, it just looks like this, where I assume I've got m features or characteristics of each record. And so what does a network look like that simulates simple linear regression and a simple logistic regression? Well, I've got m input variables, and again, I'm going to flip it so it's vertical, and I'm going to hit it with another matrix, which is just my betas. And of course, I could, if I were doing this real, I might fold this beta 0 into this record and so on. But I'm doing a linear transformation of this down to a 1 space, and that is my regression. Now, if I stick a sigmoid on the end of this part here, then I get a 2-class classifier. I'm thresholding the output so that it's between 0 and 1. I guess it's negative 1 and 1, or am I thinking tanh? Or whatever, it's the probability. It must be between 0 and 1. It's the probability of class 1 being true. At least our confidence in it. Okay, so now if I build a network that looks like this, otherwise known as a linear regression model, and I run all of the training data through this model and get all the y-hats, it looks like this. That's what that looks like. Okay, so as I pointed out here, kind of underfitting. I would prefer, probably my human eye could look at this and go, maybe something that looks a little more like this would be better, something nonlinear. So I would say this is underfitting a little bit, but it's probably pretty close. Okay. Here we go. All right, so let's try to get some more power out of this. I said these are building blocks. So let's take the output of one linear model and stick it into the input of another linear model. Surely that can get us something interesting. Turns out it doesn't. It gets us another line. And if you look at it mathematically, here's our normal transformation. We transform the input vector into some other vector. And then we run that as input into another transformation of W prime and B prime. Now these are scalars because the output has to be a scalar. And if you multiply all this out, then we combine all these terms into a scalar and call that B double prime. And we take this W and multiply it by a scalar, and we'll call that vector double prime. So once again, we get the form of a linear equation. So this form tells us we know for a fact it's got to be a line or a separating hyperplane. So this is what it looks like in structure. And if we're doing this in PyTorch code, you'll see that there's an NN for neural network package. And inside there's something called a sequential object. And that is just giving me a pipeline. It lets me hook things together. And so I've made a pipeline of 2 linear models where I have M input features, and there's 1 output from this first layer. Then the second layer takes that 1 output from the first layer and then generates 1 output. And that's what this looks like. So this is a visual representation of what this PyTorch code does. But we still get a line. And this is generated using one of the notebooks I've got. So I'm not just making that up. It's actually generated. Okay. Now, how do we actually get more power, though? If deep learning is supposed to be about multiple layers, how do we actually use depth to get more power? Turns out all we have to do is inject a small nonlinearity in between our linear layers, and we get more power. So for example, I'm going to take the exact same model, except I'm going to inject this sigmoid here. So I take a transformation of the M input features to 1 output value. I run it through this sigmoid activation function, and that gets me another single value. I run it through this transformation, and I get my regression. And so when I run our cars data through this, I get this kind of interesting, although not very good, but an interesting non-linear pass or regression line or regression surface. Now, if I use a rectified linear unit, we call it a ReLU. If I use a ReLU, what do I get? I get two different lines that are joined at a discontinuity, which is interesting. So I think of it as this getting a line and this clipping the lower part of the line off, making it 0. And then this doing something else with a line. And so it kind of, I think of it as two lines clipping, but I haven't verified that mathematically, but it's what it looks like. So I'm going to go with it. So the PyTorch representation would be make a sequential pipe where I've got a linear layer connected to another linear layer separated by a ReLU. And so what this sequential object does here is it glues these together. And this is just a matrix and a vector algebra. This is just multiplying by a clipping function. And anyway, so it just hooks all these things up exactly as you see here. Okay, there's another way to get power out of a neural network. Instead of just extending in the future, we can actually stack neurons. And so here's where we get more than one neuron in a layer. So now what I've got is I've got 5 neurons. I think of them as just 5 transformations. And so now let's say I have 3 input characteristics, number of bedrooms, number of bathrooms, square footage. So I've got 3 features and I'm transforming it into a 5 vector. Well, how do I do that? Well, each one of these blocks is a linear transformation, and it's going to take all 3 of these values. It's going to do the linear transformation on it, and it's going to put the value right there. You guys can see my cursor move, right? Somebody's nodding, somebody nod. Daniel, can you nod? I see your face. All right, smile, that's good enough. So now this neuron takes these 3 values, multiplies it by the weight matrix, and adds a bias, and that gets me the second value here. And this takes all 3 and gives me this one, and so on. Now, typically what you'll see in neural network introductory materials, billions of lines going like this, and they're all connected up, and then magic happens. That freaks out my brain. I can't handle it. I think of it as just transformations, and I don't have to think about all those lines, okay? So for each one of these neurons, I'm going to get an output. Now, you might ask, so first of all, these W and B are different, because if they were all the same, I'd get the same answer, right? So the question is, how do we get W and B to be different? Well, when we train, we're going to initialize these to be random values. So they're all going to start out different. And then we're going to perform a training that reduces the loss, and it's just going to keep these things as separate, and they'll move to different parts of this. These weights and these biases will move to different values, and then we'll get separate values out of this vector, okay? So we're going from a 3 vector to a 5 vector, running it through a ReLU, and then we're just going to combine all those using a simple linear regression. So this tail end is just linear regression, right? But I've transformed these 3 vectors, which are 3 features, into 5 features. And so now I've converted what used to be a 1, and I'm converting it to a 5. So what I'm saying is there's 5 input features, there's M input features, there's 5 output features. Run it through a ReLU. Those are 5 features going into the second layer, and send 1 value out, and that's my regression. And so when I do run this through, this is the little thing I get. And so what you see is you get a piecewise linear regression. Okay. Any questions? Should I stop for people to take a break or a breath?
Yes. Oh, you go ahead.
Sherry, go ahead.
Yes, I have a question. So how do we decide the each layer's linear combinations in actual case?
How do we decide what these W's are? Is that right?
Yes.
Aha. So that is where all of the money is. Okay, we're going to build a training procedure that figures out what those W's should be. Right now, I want you to pretend that a magic process occurs, and those are figured out automatically, and they're different in each one of these neurons. These W's are all different. These B's are all different. And so when we get to the training process, you'll see how we're going to be moving these around and figure out what the best is. Now, if you want to think about it simply, and we'll start this way in the lab, there's a whole bunch of values in here, W1, W2, W3, and so on. Think of them as your betas and your regression. Well, that gets me a giant search space. What if I just tried all possible combinations of all parameters? And then every time I get a new combination, I figure out how good a fit it is. And then I simply choose the set of weights and B values that give me the lowest cost. That would actually work. You would probably spend a few lifetimes waiting for that to complete, however. So we have to find a better way. And it turns out there is a better way, but that's a perfectly acceptable way to do it. It's, you know, just a brute force solution. You're trying all possible combinations of W's and B's and find the one that gives you the lowest loss. Daniel, you had a question?
Yeah, no, I did. Sorry, I took me a second to hit unmute. Yeah, my question was just going to be, what's the initial W, and then how do we tune it to get the the best weights for these vectors?
Okay, so for initialization, we're going to do a random. It's not any kind of random. We're going to do something special with the random values, but you can think of them as just random values between 0 and 1 or something, or -1 and 1. Okay, let's see, mine response. Okay, so now I've got a slightly more complicated model here. Oh, do I? Yes, I've added an extra layer in here. So I'm also doing a 1D. So I've got one characteristic, like number of bedrooms, or 1 pixel from an image. And because I've got 5 neurons, I get 5 output values. So I'm converting a 1 vector to a 5 vector, running it through a rectified linear unit. Then I'm converting that to a 2 vector, running that through the ReLU. And then I'm finally doing my regression on these 2 super fancy, carefully engineered features that this model has come up with for me. And I get a regression out. And so now, again, I've got 1 input feature, and I'm generating 5 output from that first layer, ReLU. Then those 5 and converting to a 2 vector. Take that 2 vector, convert it to a 1 vector, and I get my regression. And that's my output. And then here's this nice little thing I see. It's not much different than what we saw before. So we're not getting much improvement in power, but I wanted to show you what it looked like when you had a deeper and taller network. And then there's also this thing that I came up with recently called tensor sensor. And I won't go into details on it, but you can check this out. It allows me to visualize the dimensionality of the matrix arithmetic that's going on. Because when I was trying to learn this, I didn't start out using the neural net objects. I wanted to start with matrices so I fully understood what was going on. And I always got these doggone dimensions wrong. So what you can see that if I'm going from 1 dimension to a 5 dimension, this weight matrix 1 has to be, yeah, I mean, I'm leaving the B's out here, but it just has to be a series of 1 weights per output. Anyway, so you guys can look through that if you like. The second layer is a little more complicated because we've got 5 input features and I want 2 out. But if you do this vector or this matrix vector math, you see you get this dimensionality and so on. Okay, and at is a Python operator for matrix multiplication. Okay, so if more neurons are good, let's go crazy. Let's give it 1,000 neurons. Why not? Now, in some cases, this might be the right answer. In this particular case, with the particular training regimen that I did, I ended up overfitting. And the reason I say this thing is overfitting, it's overly specific. Like, is there really something about the underlying distribution, representing the weights of cars versus multiplication, miles per gallon? Is there really something in underlying physics that indicates there should be a jump in miles per gallon as I increase the weight here? Unlikely. A better fit is probably some slightly curvilinear negative log thing or negative exponent, right? It's unlikely that this is good. So that's why I say it's overfit. And I gave it so much power that it's like, oh, cool, I'm going to go chase all these little weird things in here, right? So you can't just always throw more neurons at it. And the other problem here is this is going to train a lot slower because you've got so many extra parameters, right?